In this video, we're going to take a look at the final relationship for Kw. Kw, another relationship that exists is that you can take the Ka for an acid and multiply it by the Kb for its conjugate base, and that would actually give you the Kw. You can actually see proof for it over here. If you want to see why that works out, I'd recommend you watch that. It's a pretty good video. It's just a few minutes long that shows you how this relationship is derived and how it's actually the same thing as saying the Kw is equal to OH times H2O plus. It helps you to understand that a bit more. So do watch that. But let's go try a practice problem to see how we can use this relationship. So the hydrogen phosphate ion, HPO4 2-, has a Ka of 1.3 times 10 to the negative 13 at SATP. What is the base ionization constant, Kb, for the phosphate ion? So just to show you this here, we essentially have HPO4 2-, aqueous, and it's going to be reacting with water, and it's going to produce, assuming this is an acid here because we said Ka, we're going to give away the H and it's going to become PO4 3- AQ plus H3O plus AQ. And so for this there would be a Ka, and the Ka would be 1.3 times 10 to the power of negative 13. Now what we're asking you for is this, the Kb for this one. So PO4 3- AQ, we're asking you for a Kb, so we're telling you it's acting as a base right now. It's going to take H from water, and if we're saying Ka, Kb, we're talking about weak acids and weak bases. Strong acids and strong bases, we're not really going to mention Ka and Kb because they're not governed by that. They just dissociate and ionize 100%. So we'll get HPO4 2- AQ, because this took an H, and then when you take an H you become less negative by 1, plus OH minus AQ. Now we really didn't have to do all these steps. I was just trying to show you that this part here would have a Ka, and this process here would have a Kb because this is acting as a base. And so we want to figure out what that Kb is. So what we know is that Kw is equal to Ka times Kb. So we know that that's going to be 1.0 times 10 to the negative 14 is equal to your Ka 1.3 times 10 to the negative 13 times Kb. And so if you want to solve for Kb, that's Kb. We're going to do 1.0 times 10 to the negative 13 or 14 divided by 1.3 times 10 to the negative 13. So 1.0 times 10 to the negative 14 divided by 1.3 times 10 to the negative 13. And you get about 0.0769, or so 2 sig fig 77. So this is your Kb for this reaction. Notice that your Kb is pretty high compared to your Ka, which is an interesting relationship there, right? So this is our Kb here. And if you think about it, this makes sense. If the Ka is really small, that means going this way is not going to happen very much. But going the other way probably will happen, will be favored more. So if you have a very small Ka, that means that your Kb is going to be larger because the other direction is favored. So we're going to go into more detail on that later on, but I want you to start thinking about that from that perspective. If going one way is very weak, very small, going the other way is usually a bit more favored. So Ka, very weak, very small, Kb, much bigger. But we used a relationship between Kw and Ka, Ka and Kb being Kw to solve this type of problem here. So in this video we saw the second relationship for Kw. In the previous one we saw the first relationship for Kw. You should know both in order to solve problems where you have to find the Ka versus the Kb and the OH versus the H3O+, because that will help you to solve problems involving ice tables later on for weak acids and weak bases.